Okay, this is we are going to be studying continuity today. This is my 5th video of the day here that I'm making. I'm doing all the videos for this unit. So hopefully I'll be on my game. Sometimes by the time I get here I start to make little errors. So if so, you'll have to cut me a little slack. All right, continuity. Continuity is one of our super important concepts of calculus. It is a criterion for several of our fundamental definitions and theorems, including the derivative. Okay, let's take a look visually about what continuity means. Oh, I'm going to grab I want to make sure I hit all of our little notes here. So let me grab this here. Great. Okay, so visually, continuity. Continuity visually is just if you can draw the graph of the function without picking up your pencil or your pen. If you can draw the graph without picking up your pen or pencil, then it's continuous. Okay? So it can have little like cusps. It can do lots of things, but it just keeps on going. I can draw it without picking up my pen. All right? In particular, I'm going to be having on each of my little graphs here, I'm going to denote like this value of A. Okay? Here, there's nothing funny going on at A. Okay? If you can draw the graph without picking up your pencil, for any reason, then the function is continuous. Okay? In fact, it's continuous for all values of x. We're going to be focusing on one value of x. We're going to be focusing on this x is equal to a. So specifically, I'm telling you, okay, I don't know if I spelled that right or not. Specifically, at x equals a, f is continuous since, okay, we're going to be using limits here to describe continuity, and I want you to get there right away. Okay, the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, and they are both equal to f of a. Limit from the left equals limit from the right, and the function value is right there as well. Everything is right there. They're all equal. 3 things are equal. Okay? Next up, I'm going to draw another graph, and again I'm going to have this little a value here, but this time this graph is going to have a hole right at a. So I can still have anything happening over here, but right at a, I've got a hole. Okay? This function has a hole when x is equal to a. This is called a point discontinuity. Point discontinuity. Okay? It is also called a removable discontinuity. All right? So, using limits, okay, f has a whole at x equals a if the limit as x approaches a from the left of f is equal to the limit as x approaches a from the right of f, but not equal to the value of the function at a. Okay? The value of the function may not be defined at all, or they might give it to you as being elsewhere. Either way, it's a whole. This is a whole. All right? The next one. The next one is when we have a vertical asymptote. So again, I'm going to denote my little x is equal to a. I'm going to draw a little vertical asymptote here. And I'm going to draw my graph. So I'm just going to draw it. It can be anything coming up to it, but right here, let's say that it's going to positive infinity. And on the other side, it doesn't matter what's happening on the other side. It could be also going to infinity. It could be negative infinity. It could be a straight line. It could be a horizontal line. It could be anything. Anything. This is already a vertical asymptote, even if I don't tell you what's on the other side. This is a vertical asymptote. This function has a vertical asymptote when x is equal to a. Okay, this is called an infinite discontinuity. That's an infinite discontinuity. It is also called a non-removable discontinuity. And I will tell you that we have another type. What I'm about to do next is also another non-removable discontinuity. So I'm going to say here one of two types. The next one will also be a non-removable. Okay, an infinite discontinuity. Infinite discontinuity is when, okay, the limit as x approaches a from the left of f of x is equal to infinity, or the limit as x approaches a from the left of f of x is negative infinity, or the limit as x approaches a from the right of f of x is infinity, or the limit as x approaches a from the right is negative infinity. Any of those creates an infinite discontinuity. Okay? Any of those. 4 possibilities. All right? Okay, next up. Okay, our last type of discontinuity is a jump. So again, I'm going to label A here. Okay? And we're going to have a jump. I'm going to make like something here and something here. Maybe this one is going to the point there, and this one is going up here. It doesn't matter. And I don't care where the function value is. Maybe it's right here, maybe it's right here, maybe it's in the middle, maybe it's high, maybe it's low. It doesn't matter where it is. It does not matter where it is. I'm just going to put it here just to put it somewhere, but it doesn't matter. Okay? This is a jump. This function has a jump at x equals a, okay, this is called a jump discontinuity. It is also called a non-removable discontinuity. Okay, so one of two. This is the other one. Okay, so infinite and jumps. Those are the two non-removable. Removable is whole. Okay. All right. Let's see. A jump discontinuity. At x equals a is when the limit as x approaches a from the left is not equal to the limit as x approaches a from the right. It does not matter what f of a is. The two sides are not equal. Okay? Alrighty. So, definition of continuity. Definition of continuity. A function f is continuous at x equals a if the limit from the left is equal to the limit from the right and it's equal to the function value. Continuity requires those three things to be equal. If you are asked to prove continuity, you must show three things: the limit from the left, the limit from the right, and the function value. Only if those three are equal is f continuous at that value. Okay? If even two are not equal, then f is not continuous. All right? There are two types of discontinuities: removable and non-removable. Removable discontinuity is a whole. It's the only one. Non-removable is a jump or a vertical asymptote. Okay? We just have to know those. Okay? All right, let f be a function, the function whose graph is given. State the value or values of x at which f has a removable discontinuity. Well, removable is a whole, so I'm looking for the wholes. This is a jump. This is not a whole. This is a whole. Whole. Okay. This is a jump. This is a whole. So, x is equal to 1 and x is equal to 4. Okay? Again, a whole is when the limit as x approaches a from the left is equal to the limit as x approaches a from the right, but it's not equal to the value of the function. Okay? Next up, state the value or values of x at which f has a non-removable discontinuity. Non-removable, I think a jump or a vertical asymptote. Well, I don't see any vertical asymptotes here, but I do see some jumps. I see a jump here, and I see a jump here. So x is equal to -1 and x is equal to 2. So remember, a jump is when the limit as x approaches a from the left is not equal to the limit as x approaches a from the right. Okay? Alright, next up, state the value or values of x, if any, at which the function has a discontinuity. A discontinuity. Well, for g here, I see that g has a hole when x is -2, right? And that is the only value where there is a discontinuity, and it happens to be a hole. Even if this x minus 2 was not here, x equals -2 would still be the value of x where there was a discontinuity. It would be a vertical asymptote, but it's still a discontinuity. And they did not ask me to distinguish between any, so the answer is just x equals -2, right? For this one, it's a piecewise function. So individually, this is a parabola, which is always continuous. This is a line, which is always continuous. The only value of x where there might be a discontinuity is right where these two change. So I'm going to find out. If I put in 1 for x into this graph, I get 1 squared plus 3, which is 4. If I put 1 into this graph, I get 5 minus 7, which is -2. These are not the same. Therefore, it's a jump there. It's the parabola on this side, and it goes to 4 and stops. And it's a line on this side, and it starts at, or it goes to -2 and stops. So there's a jump there. So discontinuity at x is equal to 1. Okay. Next up, state the value or values of x at which f has a discontinuity if f is this one now. Alrighty. So I'm going to do the same thing. It's a piecewise function. It's a parabola then a line. In this one, we have 1 squared plus 3, which is 4. In this side, we have 5 minus 1, which is also 4. It's still a parabola and a line, but this time they meet at the same spot, right? So f is continuous at x equals 1 this time. There are no values of x at which f has a discontinuity. Okay, which of the following is continuous at x equals 1? All right, first up we have this piecewise function. This is just a point. This is the point 1, 1. This is true everywhere except x equals 1. So I'm going to clean this up. We can factor the top and factor the bottom. Well, not factor the bottom, it's just the bottom. All right, since x is not equal to 1, I get to reduce these. And that reduces to 1. So this is equal to x minus 1 because x is not 1, right? Now if I put in 1 to the remaining x, I get 0. So this is a rational function with a hole when x is 1, right? And the hole is at the point 1, 0. The point is there, there's the hole. They do not match up, so therefore it's not continuous. F is not continuous. It has a point discontinuity. Is not continuous at x equals 1. Okay? This one. I know the denominator is undefined when x is -1. G is undefined at x equals -1. But what about at x equals 1? At x equals 1, is anything funny happening? No. But continuous at x equals 1. So this one is continuous at x equals 1. Alright, this piecewise function. If I put 1 in for the x here, half of 2 is 1, plus this one is 2. If I put the 1 in here, it's just a 2. 2 is equal to 2. So h is continuous at x equals 1, 2, and 3. Okay. All right. Another one here. I'm going to see if this is the last of it, or if I got one more page here. All righty. Okay. What value of k makes f continuous? We want for f to be continuous. It's a cubic here. It's a quadratic here. Alone they're continuous. The only place that we might not be continuous is at their changing point. So I'm going to put 1/2 in for x in the top and x in the bottom. Okay? Set them equal because we want for them to be equal. For f to be continuous, the top must equal the bottom, right? And I'm going to solve that for k. So k times, I'm putting 1/2 in for x, so that's going to give me k over 2 cubed, so k over 8, minus k over 2 minus 1/4. I'm making that equal, so I'm setting it equal to 32 over 4 minus 2. It's a little equation. I just have to solve it for k. I am going to clean up the right-hand side here. 32 over 4 is 8. 8 minus 2 is 6. Now I am going to multiply both sides by something to get rid of all my little denominators. If I multiply both sides by an 8, it'll work. So I'm going to have k minus 4k minus 2 is equal to 48. This is negative 3k minus, or is equal to 50. So k is negative 50 over 3. B. Okay. All right, just a couple more. The graph of g is a piecewise function. Which of the following statements is true? F has an infinite discontinuity at x equals 1. Infinite discontinuity is a vertical asymptote. So does G have a vertical asymptote at x equals 1? Yes, it does. Remember, vertical asymptote is if either the left or the right is going to n infinity. So that is true. Number 2 here, G has a non-removable discontinuity at x equals -1. Non-removable is either a jump or a vertical asymptote. So at x equals -1, do we have a jump? We do have a jump. That is a jump right there. That is true. Alrighty, one more. G has a non-removable discontinuity. That's another jump or vertical asymptote. At x equals 2. At x equals 2, is this a jump? No, it is not. That is a hole, not a jump. So this one is false. limit from the left equals limit to the right from the right. That's a hole. This one is a jump. Okay, so 1 and 2 only, 1 and 2 only, let's see. Okay. Which of the following functions has a jump discontinuity at x equals 3? All right. First piecewise function, I put 3 into x here. So remember, a jump, you guys, is when the limit as x approaches 3, in this case from the left, is not equal to the limit as x approaches 3 from the right. That's a jump. Oops, can't see it. That's a jump though, okay? If I put 3 in here from the left, 3 in here, that's 9 minus 12 plus 1. That's going to give me a negative 2. From the right, 1 minus 3 is a negative 2. Those are equal. So you guys, the limit as x approaches 3 on the left is equal to the limit as x approaches 3 on the right. That is not a jump. Okay? So not F. G. Get another color here. Alright, put in 3 here. Put in 3 here. Okay, 9 plus 6 is 15. 4 times 3 is 12. The limit as x approaches 3 from the left of g of x is 15. That is not equal to the limit as x approaches 3 on the right. So, jump. H. For H here. Okay, this is different. The way it's posed. It's not left, it's not equal to. It's just not equal to. Right? So this is a parabola. If I put 3 in for x, I'm going to have 2 times 9, which is 18, minus 15, that's 3, plus 2, that's 5, right? So this is a parabola, except, and I don't know what this looks like, at the point 5,3, there's a hole, right? This might fill the hole. It might fill the hole, but is it possible that this is a jump? Absolutely not. Because of the way it's posed, because of the way they made the piecewise function, it is impossible to be a jump. It's just impossible. It doesn't matter whether this fills it or not. It's still not going to be a jump. It's only a hole at best. At best, it's a hole, not a jump. The answer here is G only. Okay, and I think that's all I did. I am really surprised that I did not have. I'm going to be adding another question here, because I need you guys to have an example of a proof of continuity. I'm going to make a number 8 here. Using the definition of, or use the definition of continuity to determine if f is continuous at x equals, I'm going to have to make it up here. I'm going to pause. I want to make up a, okay, let's continue here. At x is equal to 3 if f of x is equal to this piecewise function. it's going to be x squared plus 2x minus 7 if x is less than 3, and it's going to be x cubed minus 2x squared if x is greater than or equal to 3. Okay? So use the definition of continuity to determine if f is continuous at x equals 3 if f is equal to this function. Okay. Definition of continuity. 3 pieces. I need you to show, you must show, the limit as x approaches 3 from the left of f of x, the limit as x approaches 3 from the right of f of x, and f of 3. You must show all 3 of these, okay, because that is the definition of continuity. Okay, 3 from the left, I'm using the left of 3. That's going to be 3 squared plus 2 times 3 minus 7. That's 9 plus 6, which is 15. 15 minus 7 is 8. Okay, 3 from the right. Now we're using the right side of 3. That is 3 cubed minus 2 times 3 squared. That is 27 minus 2 times 9 is 18, and that is also 8. What is f of 3? F of 3 is using this bottom equation, which we already figured out was 8, right? The limit as x approaches 3 from the left of f of x is equal to the limit as x approaches 3 from the right of f of x, and that is equal to f of 3. So f is continuous at x equals 3. That is a 3-step continuity proof. Okay? So there will be one like this on your test, most likely, and you need to show me those 3 things. If you do not have a limit on your paper, you will not get any credit because you're not using the definition of continuity. All right? Okay.